Hello, everybody, and welcome to today's session. Thank you for joining us. We know time is precious, so let's get started with today's session, Beyond Icebergs, How the Vast Database Delivers 20x Faster Analytics and AI Performance. Today's speaker is Jason Russler, Technical Director of Alliances here at Vast Data. Jason, would you like to join me on stage?
Of course I would.
Hey, Jason, how are you doing today?
I'm doing great. How about you?
Good. I'm doing fabulous. So we want our audience to be as engaged as possible. So if you could move on to our next slide to show our audience how they can engage. We encourage you to ask as many questions as possible. So please use the Q&A box over on the right-hand side. Just ask your questions. Jason will be answering those questions at the end of the session. And I will hand it over to Jason to kick us off. Thank you so much, Jason, for presenting for us.
Okay. Well, here's the agenda. We're going to talk about a number of things. I mean, we've already done the introductions, so that's done. We're going to talk about benchmarking today. This is really about performance and assessing performance and assessing value really of this product. From a performance perspective. To do that, we're going to have to talk about what we are testing, the architectures of what we are testing as well. Get a little bit into some weeds, not too deep. I'm not going to spend time there. Don't worry about it. But data structures to understand how what I'm looking at works. Then we're going to go through some actual benchmark results and then talk about some things that are going to be going on in the future here around the database and around VAST in general. So I'm just going to kick right into it and start with what we're benchmarking. So what we're looking at is the VAST database here on the right, which is a table format. It's really good at fast projection generation. What this means is you can search for data in tabular data, find it very rapidly, and return it to the client very quickly. This is a scan, filter, project operation. That is what it's really good at. It's ASIN compliant, meaning it deals with transactions very easily. So you can update records and all those record updates aren't visible to all the other clients talking to it. So it is a fully ASIN compliant table format. It's extensible, supports schema evolution. It's feature rich. We can do all kinds of things with projections and indexes, which we can talk about a little bit. Most importantly, it is low config. It is a very easy to use table format that doesn't come with a whole lot of tunables and things that you have to optimize for and balance for each use case. And the reason for this is because it's just kind of a middle of the road product. It's a very high performance product, but it runs on all flash and it runs on a very advanced data structure and ecosystem that we're going to look at. What we're comparing it to is Iceberg here on the left. So Iceberg is a table format. It's open source. It is the most popular table format to be used in an object storage environment, which we're going to talk a little bit more, that's out there in existence. This use case, this workload of data analysis of structured data has really kind of coalesced around Iceberg recently. I wanted to compare the database to Iceberg, not compare the database to a legacy product. I want to look at the two things that people are moving to and using today. And Iceberg is really that format in this particular use case. It's feature rich. Iceberg is a very nice product. It's a very nice, well, it's not a product, it's an open source project. It's very nice. It comes with a lot of features. It runs on an object store though, so it also tends to have a lot of maintenance and configuration options around it in order to make particular use cases successful. So what are we assessing? We're assessing performance. We're benchmarking. And the reason we want to benchmark is we want to show what these things can do. This is VAST. I want to know what the VAST database can do. What is it good at? Why is it good at it? People, when you go and you tell them we have this great product, this great database, they say, well, show me some benchmarks. I want to see them. And of course, they look at them and then they don't care later. They want to see the proof is in the pudding in their use case. But you have to have benchmarks. You have to have assessments. So we're going to do this by looking at the modern lakehouse architecture under with Iceberg and S3 as the object storage, and we're going to look at VAST database. The environments that we're testing in, I'm comparing Iceberg in S3 in AWS natively. So these are EC2 instances with an engine running. using the Iceberg as a table format. I'm doing the exact same thing on the right-hand side for VAST. I'm using a private cloud. This is just a hardware gear in a data center that is aligned as close to the AWS environment as possible. So we're comparing apples to apples when we look at these two things side by side. The engine that we're using, the aforementioned engine, is Trino. So we're looking at table formats. The VAST database is a table format. Iceberg is a table format. Trino is going to be the common thing between these two tests. It is a engine for doing SQL processing. It's very popular. It's very fast. It's very good. It has very good support for Iceberg, and it also has very good support for VAST, and we like it. I'm going to talk a little bit about VAST architecture here. I don't want to go deep, but we got to understand VAST and why VAST exists and what we do, just at the very highest level. It is about bringing all flash performance to spinning disk prices ultimately. So it is a way to bring flash to the masses. You can have very deep storage without paying for extremely high cost flash. We do this with a number of technologies. Like I said, I'm not going to go deep into it, but this is very much the ethos. The point of the company is to eliminate trade-offs. You can get reliability, scalability, performance, simplicity, cost effectiveness, all out of the same platform. Throw it any use case at it, and it will do it because it is flash. And we're doing this in the context of structured data today, the database. We do it with an architecture that's fairly unique. So we have a separation of storage and the separation of compute when you're talking to VAST. So the presentation layer here at the top is hardware, and it is servicing requests. And then the storage is at the bottom. And everything is connected with an NVMe over RDMA fabric. These are fairly recent technologies that have made VAST possible. The long and the short of it is we can get 10 years of life out of read-intensive NVMe that is not intended for that. It is very low-cost NVMe, but it reads every bit as fast as enterprise-grade NVMe. You just have to be careful about how you write to it, and that's why we use storage class memory in these systems to write shape. So this is the secret sauce. We can get full life out of low-cost flash and bring it to everybody. So VAST supports a number of protocols. So we do S3, we do SMB, we do tabular format here in the middle, which is what we're looking at today. So VAST as a product encompasses a lot of protocols and methods around data. Just to give you a quick picture of what things actually look like, this is about as dumb and as simple as I could possibly, as you can get. But just to be completely abundantly clear that what we're testing here is EC2 instances talking to S3 when we're doing Iceberg. Over here, when we go and we're looking at the VAST database, we're looking at hardware or private cloud talking to VAST infrastructure, tables on VAST infrastructure. These are the two things we're looking at, and they're both sort of identical on the top layer. I'm going to talk about table mechanics here before we get into results, because the mechanics are very much why we get the results that we do. I had a question about whether or not I wanted to look at this before or after we went through the results, and I decided we'd look at it before, just so the results make a little bit more sense when you see them. So Iceberg is a table format that's principally associated with object storage. So here we have files that exist on an object store that virtualize a transactional lakehouse, and this is what Iceberg does. A transactional lakehouse is data stored in the semi-structured data that's given structure that we can also read and that we can also write to. We can do updates, we can do record changes, and that's the transactional part of the transactional lakehouse. And it's accomplished through this mechanism of metadata files and manifest lists that all point to other manifest files that point to objects. So you have this not unreasonably complicated, but sort of complicated network of files that point to each other that are housed in the object store before they port to Parquet. This is how these manifest files are how snapshots are implemented. It's not really snapshots, it's transactions. Each transaction gets a log. And this is how time travel works, by going back and forth between metadata files. So, but the point of this is you're looking at a whole lot of files, and that every time you read from this database, all of these files have to be parsed to understand what Parquet data, what data we're looking at when we access a particular table, even at a particular point in time in Iceberg. And this creates a lot of latency factors. So each one of these accesses is going to be 20, 30 milliseconds before you drill down and you start doing things. And this really affects the performance of some of the benchmarks that I'm going to look at here later. Even when you get down to the Parquet layer, you'll hear things like we have predicate pushdown in this this particular connector in Trino. Predicate pushdown, when you're looking at Parquet data, doesn't exactly mean what you might think it means. It just means that the Parquet reader is asked to read some data, and that it's going to figure out how to minimize the accesses to Parquet to bring as little data across the wire as you can. But if you're accessing random data, like a column isn't sorted or ordered and you're accessing random data, there's really nothing you can do about it. Your pushdown is going to go in, it's going to read a whole bunch of row groups, it's going to read all that data back to the engine that's then going to sort through it to find what it was looking for. If your query has a filter associated with it, like I want to find a small number of records out of a very large table, you're going to read a lot of data out of Parquet to the engine before you find what you need. And so this is a lot of little IOs and things that are going on in order to do this. Reading from Parquet is very good for throughput. Like if you just want to start at the beginning and you're just going to do a sequential read and get back to the engine and you need all that data, you can get data as fast as you want from Parquet. I'm not going to go deep into this, but this is the vast database. This is sort of a look. What I really wanted to impress with this particular slide was that the vast database exists as tabular data, or is tabular data, in a vast storage system. It's not containerized files. It's not a container that sits and gets arranged similar to Parquet or something sitting on the vast storage array. It is its own virtualization layer for presenting tabular data. It exists in the B trees that are housed on VAST, and it uses a 32K block size at the bottom when you get to the data. That 32K block size is super important moving forward, because it is a super optimal size for dealing with records within VAST, for parallelization and for throughput on reads. And so what we get with that 32K block size is when we update records, we get very little write amplification. Unlike when you update something ultimately in Iceberg, you're going to be rewriting a gigabyte Parquet file at some point. With VAST, it's all 32K chunks. You're not doing all this write amplification, so we can actually do a transactional workload. It's great for throughput. IOPS equals throughput in this case. If you just want to start the beginning of a table and just read the whole thing, we can do that too. And so we have throughput, and we can do lots of fun things for filtering data and finding it quickly when we control the data structure like this. That's all I really wanted to go. We could talk about that slide for forever, but we're going to move on to actual benchmark results now that we're 15 minutes in. So benchmark results, we ran several. You can't really just run one or two benchmarks. You have to run a few in order to get a clear picture of what you're doing with the system. The first one is TPCDS. TPCDS is a decision support benchmark created to measure data warehouse performance. These are traditional decision support systems that run in, going back to the 90s, specialized database systems that looked at, that did analysis, and that's what this benchmark is for. I did no table optimizations for any of these benchmarks. I did not optimize, sort, index, partition, anything for either the VAST workload or the Iceberg workload. I could have easily in both cases, but I wanted to keep an apples to apples look. I just wanted to show raw capability here of these two platforms. Main factors are going to be CPU utilization. There's a lot of CPU utilization in this benchmark, and there's a lot of IO bandwidth and work that goes on. So we get our first graph. So these are the TPCDS results. I ran on 3 concurrency factors for each test for Iceberg and for database. So the blue are the vast database timings. The orange are the Iceberg timings running in AWS. For the bars, that's the time. For the lines, that's the CPU utilization. Lower is better in this graph. You want this test to take less time. We got over a 30% gain over Iceberg using scale factor 4 when we did this test. And as you increase the scale factor, the delta goes up. Fast gets faster and faster and faster vis-a-vis Iceberg in this test. And the reason is because there's reduced memory pressure on the systems. There's reduced bandwidth from the storage to compute. You're not duplicating things as much. We're going to look at that here in a second in the next benchmark, why that's the case. And so we get good results. Now this is not mind-blowing night and day result. This is a really solid result on a very well understood benchmark that is optimized very well for everything. That was TPCDS. The next benchmark I ran was a filtering benchmark. So we did this by creating tables of varying sizes. I included 3 or 4 table sizes here in this presentation, from 1 billion to 1 trillion rows, 13 columns across, and we would run a filter, a predicate, a scan filter project on this table to filter out 0.001 and 0.0001% of the rows out of the table. We could present the table in rows per second. How quickly can we return that data? We filter only on one column, that's one predicate, and we return all the columns. So filtering mechanics, storage latency, processing power, and network bandwidth are all going to come into play when you run this benchmark. I have 2 sets of results for the benchmark here. This is the 0.01% benchmark. We take a trillion rows out of a table here, and then we read back that small percentage of the records. So the top graph here, these are both the same tests, different data. We have the test for 1 trillion rows, or 1 billion rows, 10 billion, 101 trillion rows. So we get about a 500% performance boost over Iceberg, meaning we run this filter, we get it back at, what we're looking at 250,000 rows a second, that rate from the vast database, versus, I don't know, that's like 30, we're getting up to 50. We'll just say 50,000 rows a second because it's on that line that we're getting back. Why is that? It's because on the vast array, we're just much more efficient about finding the data and returning it to the processing engine, in this case, Trino, than Iceberg is, because Iceberg is reading Parquet data. This bottom graph is on a logarithmic scale. So these are, even though orange and blue look like they're fairly close, they're actually orders of magnitude off. In AWS, those Trino instances were reading from S3 around 30 gigabytes a second of data in order to achieve this 50,000 row a second result. Vast database was moving a little bit over 10 megabytes a second in order to move 250,000 records a second. So this is a 500% performance increase for this test. This next slide is the same test, filtering out even less data, an even smaller percentage of the data. And Vast returns it at between 60 and 80,000 records a second to something I can't even read here for Iceberg. And then we look at the data, how fast is data coming across the wire to the engine? We are at still 30 gigabytes a second here for Iceberg, and we're just below 10 megabytes a second for Vast. The reason I put these 2 slides is to demonstrate, one, the first one, an unconstrained environment, networking environment for AWS, meaning when there are no bottlenecks in this particular test, and we have a 500% performance improvement. But the second we try to read even less data, we try to narrow things down, and these are very common in AI use cases, to read small data sets out of very large ones. We don't have the network bandwidth. This is network constrained at this point. Vast is just kind of sipping across the network line and still returning a fast row per second result. And AWS, S3, you have to read so many gobs of data from S3 that you're just spending all your time in network. So we have a 2,000% performance advantage here. So this is just an example of the very real problems with filtering large amounts of data and doing lakehouse type activities or workloads in Iceberg. So that was a good test. I got two more here. This one is a transaction benchmark. It's a very, very simple transaction benchmark. All I'm doing is updating 100 rows at a time out of a 1 million row table. I'm updating a single value, and I'm updating based off of one predicate. Update table where whatever, and then I change value. So these are 100 records get updated at a time per SQL transaction, and I do this 1,000 times. I'm updating different sections of the table. So I do this to Iceberg, and I do this to Vast Database. So these are two charts that show the exact same thing. The first one is on a logarithmic scale, and the bottom one is on a linear scale. And I had to include both so you could even see what was going on. So when I did the updates on Vast, we get sub-second 100 row updates with VDB to start on the first transaction. And then we get 4-second updates as things go to start with on AWS. So what we're showing here is just how quickly a transaction happened. And this all maps back to that earlier slide where you saw how many things have to happen before you get to a record in Iceberg, and how many manifests, lists, and things and objects have to be altered each time you make a record alteration. So you do an update in Iceberg, and you're going to get new manifest files. You're going to get new Parquet files that now supersede the old ones. And then you do this 1,000 times, and then you're piling up records and records and records that have to be parsed for each subsequent query. So this is the classic small files problem in Iceberg. That's what this replicates and what it demonstrates. So you just get this linear increase in time until such time as you decide you've had enough, and now you have to do some table maintenance and rewrite your data set, and then rinse and repeat and start all over again. So that's kind of difficult. You don't really want to. That just kind of tells you that the transactional lakehouse doesn't really exist in Iceberg, and people don't really use it this way for precisely that reason. Vast Database, we can actually put transactional workloads on it, and in some cases, you can have operational type workloads running on Vast Database alongside the analytics that are happening at the same time on the same table. So that's just a stark demonstration of what you can do with the Vast Database and still maintain the performance on the analytics side, in Vast Database versus an object-based system. I don't want to pick on Iceberg here. I know I'm talking about Iceberg all the time. Iceberg is an excellent format. It does what it does very well, but it is still predicated on object storage in the background, and that's always going to have these type of latency-sensitive limitations. I have one more test to look at. This is one of the funner ones. This is using a GPU to accelerate a warehousing workload. This is the same database. This is the same benchmark as the first benchmark that I showed here, which is the TPC-DS result. So this is a TPC-DS result running in Spark, another supported engine. The database talks to Spark as well, or can be worked through Spark as well. Using NVIDIA Rapids, which is a GPU accelerator for Spark for doing Spark workloads, and in this case, Spark SQL workloads. So we can accelerate with GPUs SQL workloads. This is a smaller scale test on a smaller system, but it is the same benchmark of 1 terabyte. This is one simple, easy slide where we show 5 results that were tested in this particular environment. We had Parquet data that was using a Hive metastore using Rapids, unaccelerated in the yellow bar. Vast database, or excuse me, Vast S3 is the S3 target, which is a very, very rapid S3 target, incidentally. So these are results that would probably be slower in AWS than they are in Vast. But we have 2 results here, yellow and brown. Yellow is the unaccelerated, and brown is the accelerated Parquet-based benchmark. I did one Iceberg benchmark. That's the purple here in the middle of the exact same benchmark, and got this result. Incidentally, longer is longer to run the benchmark, which is worse. You want these to be short. I included Iceberg just to have a baseline, so sort of we understand what it looks like with the rest of the data, particularly what we've been looking at today. Iceberg is not supported by Rapids at this time. It's almost supported, but not quite. But that's what an unaccelerated Iceberg looks like. And we have light blue here at the bottom for vast database with no acceleration. And then we have vast database with Rapids. And so we get this extremely abbreviated runtime when we combine GPUs and vast database. They complement each other very well to get a really good result. So moving forward and summing up. So vast database on a warehousing workload, we get 30% faster and greater. And as you increase the concurrency, that goes up. The reason that goes up is because memory pressure goes down, data across the wire doesn't compound when you're talking vast database between the engine and the storage. And high concurrency workloads are the norm. That's what happened. So you're going to have these deltas get really wide. I'd like to test even higher concurrency now that I know this. We can get 500 to really the sky's the limit, better performance at 500 times or 500% or 5 times 500% faster to really the sky's the limit to random IO filtering, just random filtering, to get data out of a table. This is due to filtering mechanics on VAST, which are very good at selecting data, and it's also due to network limitations as you go up into the, or as your data set gets larger and larger and larger and larger. You can't have terabyte a second networks. It'd be nice, but they don't exist, in order to service these workloads. So for filtering data, it's the sky's the limit there. That VAST can really deliver on that. Transactional workloads are the same story. So we got 1,000 to 5,000% faster on transactional workloads because that's not even fair. We're fundamentally made for it. Whereas on the Iceberg use cases, where it's just sort of something you can do, but you wouldn't necessarily want to. So, object storage is good in Iceberg's case for servicing I/O if you're just reading things. But vast database can do both. We can deliver the I/Os per second. We can deliver the throughput and create a truly transactional warehouse. So coming soon. I'm not even half done. We're not even half done with performance and figuring things out and really kind of showing what this platform can do. Not even close. So this paper that this session is based on, and this session will get an update later this year with a lot more goodies. The first one is Kafka implementation, which is coming out here in VAST very shortly. So this is where VAST acts as the brokers for a pub subsystem, and the backing store for that pub subsystem is VAST tables. It is the database. So when something is produced, it goes right into a table that is then immediately accessible by all the other engines, really reducing data engineering tasks and simplifying the environment and kind of bringing all these protocols really close together so that you can work with them seamlessly. A second thing is I didn't test any of the features in the database. So we have the capability to have fully sorted tables. This means, tables will be sorted projections of the tables, basically multiple copies of the same table sorted in different ways, but transparent to the client. So this is going to be, when I do that, this is going to be another unfair, well, of course it's fair because it's there, but it's going to be mean. These tables are going to be super fast when they're sorted like that. The nice thing about that and the point behind it is extremely easy for a user to go in, click on some columns, click on the sorting columns, and be done with it. And they have done all their data engineering, as opposed to dealing with an object storage-based system where you are rewriting the data over and over again. You're going through very complicated processes, and that's that. So, and then we have a vector database that's going to be coming out here. So a fully scalable vector database that's kind of foundationed on the same technologies as the database, and we're going to have to cover that here in the near future as well. And that's actually it for me. I am done.
Okay, so it seems like you've been a really great educator, Jason, because we have no questions. If anybody has any last minute questions, please feel free to put them into the Q&A and Jason can answer those, or I mean, yeah. Or I mean, Jason, are there any common questions that you receive that you want to answer just here at the end of our session?
I find that these, when I discuss this, it is a little overwhelming. There's a lot of information. It's very dense, and I think that there's just a lot of thinking that has to happen before you can go after. I mean, because we went through architecture and protocols and environment and the actual tests, and when someone's just kind of yelling at you that quickly over so many different subjects, it gets a little overwhelming. But I'm kind of hoping I brought the points across.
I mean, well, this isn't the only chance for people to, there was a lot of information that that everybody is, that Jason walked you through. There are other opportunities for you guys to ask us questions. So we have a live demo that we present every Tuesday and Thursday. Thank you. Good stuff. Thank you so much to Jason there. So yes, a weekly live demo every Tuesday and Thursday. You can visit us at vastdata.com/demo. They tend to be very small groups, and they walk you through our platform, and you can ask questions. It's again, very small groups of people. A lot of people bring their own work challenges to those sessions, and you can also access a real vast cluster. You can scan that QR code at our Cosmos community. So again, we really appreciate you guys joining us today. We know, again, time is precious, so we appreciate you guys joining us. Everybody have a lovely rest of your day.
Bye.
Bye, everybody.